Alright, hi guys, this is your chapters 10 through 12 review for anatomy. Um, let's start by reviewing that there's three types of muscle that we've talked about several times now: skeletal, cardiac, and smooth muscle. The major differences are that skeletal is voluntary, cardiac and smooth are involuntary. You're going to see striations with skeletal muscle. I don't like that they list striations with cardiac muscle, but they do. And then smooth muscle is going to have this fusiform shape that's pretty distinctive. If we look at the image of skeletal muscle, you see the striations here. You see the nuclei are typically pushed off to the side, and then you can see this is an entire muscle cell or muscle fiber. We'll talk about what's in there in a little bit of detail here in a minute. And then you have the cardiac muscle and smooth muscle. Again, with cardiac, you see the intercalated discs. You're going to see the nuclei kind of toward the middle. Remember that these are communicating with each other by gap junctions. And then smooth muscle, the fusiform shape is really the giveaway, and the lack of striations. I would be sure that you can identify all three of these again on the exam, kind of like we did on exam 1. You need to know the difference between endomysin, perimysin, epimysin, and fascia. Simply, the fascia wraps an entire muscle group. It's going to be a really thick kind of connective tissue. The epimysin actually sits under the fascia. It's a little bit thinner. The endomysin is going to wrap the individual muscle fibers or muscle cells within here, and then that perimysin is going to exist around a group of muscle fibers, also referred to as a muscle fascicle. The nerves, arteries, and veins are going to run within the perimysin here. We talked about different kinds of attachments, indirect attachment versus a direct attachment. Remember that both have some kind of ligament between the muscle and the bone. It's just more obvious in the indirect attachment. You can think of the Achilles tendon when you think of the indirect attachment, and then the direct attachment is going to be something like part of brachialis, which attaches to the humerus, and you can barely see the ligament there. And then an aponeurosis is simply a tendon that comes from a muscle, and it's quite broad. So between frontalis and occipitalis on the skull is going to be an aponeurosis, and then the Achilles tendon is another aponeurosis. And remember that muscles can attach, bone to bone, or tissue to bone, or even tissue to tissue. We've talked about origins and insertions a little bit. You will need to know some origins and insertions for the exam. Things like the quadriceps muscle, the origin and insertions of all the muscles of mastication. There's 4 of those, and we'll cover those here in a little bit. Just remember that the origin is typically the stationary side and the insertion is typically the mobile end, but that doesn't always hold true in examples like the quadriceps muscle. I show you this slide simply to note the prime mover, which is going to be the muscle that produces the main force, and that term does come up over and over again throughout these 3 chapters. And then intrinsic and extrinsic. I know this has been quite confusing simply because you really need to think of intrinsic and extrinsic in your own way in certain cases. You need to set your own definitions. Or you need to categorize them your own way, I should say. But really, intrinsic is the origin and the insertion are within a particular region or organ or area, and extrinsic is either the insertion or the origin are outside of a particular region. And I keep using the tongue muscles as an example, because actually all 8 of them are intrinsic to the head, but really only 4 of them are intrinsic to the tongue itself. So if you think about that difference, I think you can come up with categories for most stuff on your own. We spent a little time going through the details of what a muscle fiber looks like, and recall that it's simply a cell. The sarcolemma is really the plasma membrane of that cell, and then the T-tubules are extensions that go into the cell itself and help equalize the conduction throughout the cell. So, once that signal comes from the neuromuscular junction to contract, you want to spread that signal throughout the cell as quickly as possible, and you do that by extending your plasma membrane or your sarcolemma throughout your cell. Within the sarcoplasm, that's where the fibers are, and we'll talk about the fibers here in a little bit. And remember that glycogen is stored within a muscle fiber, and then the muscle fiber also stores oxygen by binding it to a protein called myoglobin. And then the sarcoplasmic reticulum is simply a type of endoplasmic reticulum. The muscle fiber does have rough ER and smooth ER, but it also has a slightly modified type that we call sarcoplasmic reticulum. And today we talked about Nissl bodies in the brain. That's a modified type of endoplasmic reticulum. So the same structure has different functions in different cells and gets called different things. And this is where calcium is going to be stored, so that when you do have a muscle contraction, it can be released, all at the same time. So for the filaments, remember that there's thick and thin. Thick is myosin, thin is actin. Let's go here actually. The thick filaments are myosin, so they're the kind of golf club looking proteins that walk along the actin, the thin filament here. Tropomyosin and troponin are regulatory elements that sit on the thin filament on this actin. I don't think I'm going to ask you to know any details about that, but I just want to make sure that you've heard those terms before. Going back, I wouldn't worry about the elastic filament. We'll talk about dystrophin here toward the end, and that's really the only other fiber or filament within a muscle that I'd want you to know. Again, skeletal muscle cells, they are striated, and then you do see these A bands, these I bands, the Z line and the H band. So if you look at this image, I think you would see this image again, and it'd be in the context of a question like, during a muscle contraction, which of these bands is going to get smaller or narrower? And since the myosin and actin are going to walk towards each other on a contraction, you would say the I band is getting smaller or narrower. The Z disc is just where the actin filaments connect to each other between muscle fibers. Remember, in a muscle, it's not just one giant fiber. It's groups of these small muscle fibers that kind of stitch together, and they're stitched together on this Z disc. Today in class we talked a little bit about the neuromuscular junction. We started that discussion here, and the really big thing is that the neuron is going to release neurotransmitters into this synaptic cleft, which is then going to trigger the contraction here of the muscle cell. And when you're talking about nerve to muscle, to skeletal muscle, you're talking about acetylcholine as the neurotransmitter. It is important to remember that one nerve does innervate multiple muscle fibers, but they're not all fibers grouped together. So this is an oversimplification. This nerve may innervate this muscle and then another muscle fiber 100 muscle fibers away, right? You need to remember that it's spread out. It's not all grouped together. And that's really important, because when a nerve dies, those muscle fibers are going to die eventually also. So you want to spread out those connections. You don't want everything dying in the same group or in one group. As far as contraction goes, I would recommend that you review it and understand kind of the general idea. I'm not going to ask you any specifics about this. I may ask something like, where does the calcium, where is it stored in the muscle fiber? And you would want to say sarcoplasmic reticulum. Or I may ask something like, the myosin, is it the myosin or actin that's actually doing the pulling, if you will, along those fibers? And you do want to say myosin in that case. No really serious details, just a general overview would be good. And here's an image that the book had on that. Remember that muscles can grow and they can atrophy, so if you don't use the muscles, they will shrink, but through normal everyday activities you shouldn't undergo serious atrophy. Only in pathologic cases like a spinal cord injury will you then start to really lose a lot of those muscle cells, those muscle fibers. Then we talked about two different classes of muscle fibers, the slow and the fast. The real key here is that slow is going to have more mitochondria, and they're going to be able to function for a longer period of time, whereas fast is going to have less mitochondria, but they're going to be more powerful for a shorter period of time. And then remember that fast can be further divided into a slow-like muscle fiber, which I use the example of marathon runners can actually train their fast muscle fibers to act like slow muscle fibers. But remember that a slow muscle fiber, at least as far as we know now, can't really be trained into a fast muscle fiber. That stand to be proven wrong on that. But here's cardiac muscle again. Again, note the intercalated discs and the connected, I guess the odd connections between the cells. And then smooth muscle, again, fusiform shape, no striations. These should be pretty obvious to you at this point. And then we talked about a couple of diseases, specifically muscular dystrophy, which is a defective dystrophin gene, and that codes for the dystrophin protein. And just to show you guys what that's going to look like, so this is the sarcolemma, so this is the plasma membrane of the cell, and then dystrophin here is going to connect to actin within the muscle fiber, and then link that actin to the sarcolemma, to the plasma membrane. Don't worry about all this junk here. Just note that dystrophin is this really long molecule that's linking these things together. So you can imagine that when you have a problem with your dystrophin molecule, you're going to have a problem connecting your actin to your plasma membrane, and eventually out to the extracellular matrix here. And we talked really briefly about myasthenia gravis. The only thing I would note here is, it's autoimmune. I don't really think that you need to know anything beyond that. And I am going to pause it here because this file is getting really big and start up again on chapter 11.